All right, class, Athir Mahir here. Welcome back. So over our last few sessions, we have put together piece by piece this incredibly complex architecture of a large language model, right? We've talked about how data becomes geometry, how attention creates context, all the building blocks. But today, in our final part, we get to the real magic. We're going to answer the biggest question of all. How does this thing actually learn? So think about it. We have built this machine, and it has literally billions of tiny knobs to tune. You know, all those weights in the Q, K, V, and MLP matrices we've been talking about. The real challenge isn't just bolting it all together. It's figuring out how to set every single one of those billions of knobs to just the right position. Out of an almost infinite number of combinations, how do we find the one that works? Okay, so how on earth do we solve a problem that big? Well, before we dive into any of the heavy math, let's start with an analogy. I think it's really the only way to get your head around a process this complex. The goal is simple, really. We need to find the lowest point. I want you to picture a mountain range, but, not a normal one. This mountain range doesn't exist in 3 dimensions. It exists in hundreds of billions of dimensions. It's kind of mind-bending, I know, but just go with it. Every single point in this landscape, every coordinate is one possible configuration for all those billions of parameters in our model. And the altitude, how high up you are at any given point, that's our error. That's how badly the model is doing. So what's our goal? Simple. Get to the bottom. Find the deepest valley in this entire vast landscape. This theoretical landscape, it has a name. We call it the cost surface. And it's pretty intuitive, right? A lower altitude, a lower cost, means a lower error rate, and that means a much better model. So that naturally leads us to the next big question. Okay, fine, but how do we actually measure our altitude? How do we know how high up we are? All right, let's get into the mechanics of it. To navigate this crazy high-dimensional mountain range, we really just need 2 things. First, we need a map that tells us our current altitude. And second, we need a way to figure out which direction is downhill so we can take a step. So that map I mentioned, that's our cost function. You can think of it as a very precise mathematical formula that gives the model a score for every single guess it makes. For a language model, this usually boils down to looking at the probability it gave to the word that actually came next. We use a neat trick called negative log probability, but don't worry too much about the name. All it does is turn a high probability for the correct word into a really low error score, and a low probability for the correct word into a really, really high one. And this table here just lays it out perfectly. Look at that first scenario. If the model is confident and it's correct, let's say it gave a 99% probability to the right word. The cost, or the error, is basically 0. Great job. But now look at scenario B. What if it was confident but totally wrong? It gave only a 1% chance to the word that was actually correct. Well, in that case, the cost just shoots through the roof. It's the model's way of screaming, "Whoa, I messed that up badly." It's a huge signal that something needs to change. Okay, great. So now we have our map. We know our altitude. We can tell exactly how wrong we are at any given moment. But which way is down? I mean, with billions of different directions to move in, which knobs do we turn? And do we turn them up or down? That, my friends, is where the magic of calculus comes in. This whole process is called gradient descent. And here's how it works in a nutshell. For every single example you show the model, it uses calculus to find what's called the gradient. Just think of the gradient as an arrow that points in the direction of the steepest downhill slope. It's the single best direction to move to reduce the error. Then it nudges all 1 billion plus of its parameters just a tiny, tiny bit in that direction. And then it does it again, and again, and again, literally trillions of times. And this is so important to understand. Learning for an LLM isn't one big aha moment. It's not a flash of insight. It is the result of trillions of these tiny calculus-guided baby steps. It's a slow, steady, iterative crawl down that massive cost surface, always trying to find a lower point. So that's the learning process. That's how it works. But this brings up an even bigger question. Why this specific architecture? Why the transformer model the one that has completely taken over modern AI? The secret, as you're about to see, isn't just about the math it does, but the way it's designed to do it. If you think back to what came before, models like recurrent neural networks, they read text the way we do, one word at a time, in order. It makes sense, but it's slow. The transformer, and we talked about this back in part 2, just threw that whole idea out the window. It looks at the entire passage all at once. And that simple change unlocked a superpower: massive parallel processing. Now, this design wasn't an accident. It was absolutely revolutionary. Why? Because the kinds of calculations the transformer does, all those matrix multiplications in the attention mechanism, are the exact kind of work that modern GPUs are built for. GPUs are amazing at doing thousands of simple calculations all at the same time. It's this perfect marriage between the algorithm's design and the computer hardware that lets us scale these models up to just insane sizes. And that word, scale, brings us to the final and maybe the most powerful idea that has driven almost all the progress we've seen in AI over the last 10 years. It's a surprisingly simple concept, almost a brute force approach really. It's called the heuristic law of scale. It's a fascinating observation, and we've seen it play out again and again. What it says is that as you make these models bigger, more parameters, and you feed them more and more data, they don't just get a little bit better at what they do. That's not what happens. At certain points, they make these incredible qualitative leaps. They just suddenly develop entirely new skills and abilities that you didn't explicitly train them for. And here's the kicker. Here's what makes this insane scaling even possible. Remember the model's basic job? It's just predict the next token. Because the task is that simple, it doesn't need people like you and me to sit there and create perfectly labeled training data. No, it can teach itself using the biggest dataset humanity has ever created, the internet. It's this massive, messy, unsupervised textbook. I mean, just look at that number. We're not talking millions or billions. We are talking about trillions of words and pieces of text. By chewing through that colossal amount of data, the models aren't just learning grammar. They're learning statistical patterns, facts about the world, how to reason, the subtle nuances of human language. It's all in there. And that brings us to the end of our journey. We've covered a lot of ground, haven't we? We started with how data becomes geometry. We dove deep into how attention creates context. And today, we saw how calculus and just unbelievable scale make learning possible. This law of scale, made real by the transformer architecture, has brought us right here to this incredible moment in history. And so I'll leave you with this question. For all of you who will be building the future, what comes next? What's the architecture that will define